have your book open to the 3-2 section. We're going to go through several of those examples today, not all of them, but that way you can just screenshot those examples. I think it'll make it a lot easier. But as you guys already know, when we're dealing with exponents, we're dealing with logs, whether they're natural logs, traditional logs. The way that you differentiate those, there's a bunch of tricks and rules to them, right, that you have to know. And so it's just a matter, we need to visit those. And then we're going to, of course, create situations where exponents have polynomials in them, and so we have to chain rule on that. And then there's some other ones with absolute value stuff that we'll look at and we'll go through. And then there's some equations that technically are implicit differentiation. And I'll explain it as if you don't know implicit differentiation, but it's pretty straightforward. So we're just going to go through a bunch of examples today. Okay. So first of all, and again, write down what you need to. Like finding the derivative of e to the x, we know that that's e to the x. So it follows if u is some function that not only is it work out the same, but then you have to take you have to differentiate the variable, right? Or the polynomial, whatever that power is. So you sort of, here's my traditional piece, right? This part is the same as over here, but then you have this u that you have to take care of, and you have to find the derivative of that u, and you multiply it. One of the things that is going to be, I still can't decide when to stop and when to switch stuff around, and so you'll see that some of my examples that I have written up here, I go another step because I just don't like the form that it's in. And it's fine if you leave it in the first form and stop, but there's that part of me that still I can't let go of it. I want to put it around, and I want to put the numbers in front and the descending order and all that stuff, and you don't have to do that. But I can't stop myself from doing it, so I continue to do that. Anyway, all right, here are the first two examples. This one is example 1 from the book, example 6 from the book. Go ahead and differentiate those. Let's just see that, make sure we know what we're doing here, and then we'll kind of go from there. So both of these are basically the same, right? We're talking about e to some power. So this part is going to be there still, and then you just have to differentiate the power. Now, I went ahead, this one was straightforward. This one I changed, I believe, but we'll go through it one at a time. So again, it's my derivative is just the same thing, e to the whatever power, and then you just have to differentiate the top, and that's 2x plus 3. So here's what I was talking about. Like, this is fine. You could stop here. Make sure to put the parentheses, though. I know some of you guys are talking about parentheses over here. You just don't want to leave the 3 from being multiplied, but this is where I can't help myself, where I have to put it in front because it just bothers me. It's fine if you didn't, okay? And it's fine if you didn't put the multiplication symbol, but the power, be careful. You just don't want to, accidentally make this power seem like it's at the same level, or that this coefficient is, at the same level as the power. Just, you watch your line for a bit. Okay. Over here, like I said, the first thing I did is I get rid of this and convert it to negative powers. It just makes differentiating this easier, okay? So obviously that part's there, and then when we differentiate that, we just get 3t to the negative 2, again. And now I even can't help myself here, so like I move the t squared back down, you don't have to do that. Either of those is fine. I just can't help myself. I don't know. To me, this looks nicer to me than this. This feels uglier to me. But it doesn't matter. Ugly is fine also. So as long as they're equal, it doesn't matter.
I'm so glad you feel that way.
No, I'm sorry. It's the best I got. All right. Any questions on those? All right. Let's get into some other ones. We got a few to get through. So when we talk about taking the derivative of the natural log, again, pretty straightforward, 1 over x. And then if what's next to the natural log is a polynomial that can be differentiated. We have to differentiate that too. You have two different ways of looking at it. You could write it like this, or you could leave it like this. Again, this is kind of personal preference. However, a lot of times with problems like this, there'll be able to be some simplifying going on, and you can reduce, and again, you're talking about answers that look nicer. Not that are necessarily better, but they're cleaner, less ugly. Okay. Now, this I'm going to give you. We're going to go two. We have the same problem. We're going to differentiate it two different ways because one, just to demonstrate it can be done two different ways, but two, I think sometimes there's an example, part of the example that I think is helpful to see. Okay. So this is example 2, and maybe you're saying, why did you put this? Why do you even have to say I have to use this? And you'll see why in a minute. Okay, so basically what we're saying here is use this. Don't use a log property to come up with a number. So go ahead and differentiate that. Let's see what you end up with. I do want you to simplify it as far as you can too. Here are the steps, right? So it's basically the derivative of, it's 1 over 3x, and then you have to take the derivative of the top. So it looks like this, right? So 1 over 3x with the derivative of 3x on top, 3 cancels, so I get 1 over x. So now, another way to look at it, and again, this is the reason, there's a reason that I'm going to show you in a second that I want you to pay attention to, okay? This time we could do the same thing using log properties, okay? And so if you had wanted to originally, you could have, whenever you take the log of something that's being multiplied together as a product, you can split it up into two terms where they're combined by addition, right? This is the old log properties from Algebra 2. And the reason I want to show you this is because sometimes we get to a place where we forget what natural log of 3 actually is. Like what it means. What does the natural log of 3 represent? A constant, right? It's e to what power equals 3. And so whatever that number is, when there's not a variable in it, that just ends up being a constant. And you say, why, who cares? Why are you telling us this? Why are you going through it? Because when you take the derivative of that constant, right, what is it? 0. So in reality, what I'm doing here is I really only have to take the derivative of natural log of x, because this just drops out, which of course we know is 1 over x. We already knew the answer, but I think it's important to revisit that sometimes. There are moments, intellectually, you have moments where you forget the easy stuff, right? The natural log of 3, you get so into the weeds with some of this difficult abstract math that sometimes we forget the easy stuff. And so that's why I think it's just important to visit that. In review. So, all right, next, more exponent properties. Okay, now if I'm taking the derivative of a constant raised to a variable, so the base is a constant, that's what a represents there. Okay, so this is where it's the same thing, a to the x, and then you also have to multiply it by the natural log of that constant, whatever it is. Okay, now what will happen is if the power isn't just a variable, right? The top one is the simplest example. Of course, if the power is some type of polynomial, you must also multiply it by the derivative of that power. That's really the only difference. From there, this change right here is the only thing that is added in. Just make sure you have the derivative of the power also in there. Simple enough, right? The chain rule is just kind of, regardless of the situations, it's like that inside, that inner term, and you just have to make sure that you always find the derivative of that inner term, whether it's in a power or it's in parentheses or wherever it is, okay? Well, here's a simple one. Go ahead and do that one. I think it's just a matter of making sure you went far enough, right? My first move, of course, is going to be what? What should I do first? Huh? Yeah, I'd write it as v to the 1/2 power for sure. Get rid of that radical. And then be careful again, because now we have different layers of powers, right? So we're going to have this as part of our answer. This is going to be there. Natural log 3 is going to be there. And then I just need to make sure I take the derivative of v to the 1/2. And so there's my first part. That's still there. Why I chose to rewrite it in the original form, I don't know. I really would probably normally say natural log of 3 next, but I just followed the order that they put this in. So when I take the derivative of this is 1/2 times v to the negative 1/2. Okay, and then last, natural log of 3. I think that's all I did. Did I stop there? Yes, I did stop there. I couldn't help myself here, but everything else I just left alone. Okay? Questions on that? Y'all have some equivalent form of that? Pretty straightforward, right? So, but as we go through these, it's like, okay, there's another thing I have to memorize, or or recall in your case, probably instead of memorize, but it's another form, and here's still another form. Okay? When you just have a regular log, it could be the common log, so they wouldn't write the a. So if that's not there, then you understand that the base is 10. But here, it switches from logs to natural logs, right? The x goes down, natural log of the base goes down, it's all under 1. And again, so the only difference is if this is some other polynomial, it's the same thing, except you have to include the derivative of that, right? So it's just another format that you gotta know. This is sort of the parent form, and this is sort of the transformation, so to speak. Okay? Here's another example. This is example 11. Now, of course, I changed it up a little bit. Well, they changed it up, and I chose to change it up. Did you guys compare answers to each other? Do that. Yeah? Good? All right. So, again, we're finding the derivative. All right, so my x term, my u term, goes down here, natural log of 2. Then I just have to take the derivative of this, which is what? What is the derivative of x squared plus 1? 2x. Okay, so that's the actual derivative. Then I just have to plug 2 in, and we're good to go. And so I get 4 up top, 5 natural log 2. You could stop there. Again, I couldn't help myself. What do you think I did? No, I did not do that. I could have done that, but I did not do that. Yeah, so okay, let's add that one in there. So I could have said 4/5 natural log 2. I could have done that, yes, but I did not do that.
You can't add the 1 with it.
Yeah, that'd be in the numerator.
Oh, you're right. No, all right. All right. Kirk tripped me up, and I didn't even catch it. Good job. No, you can't do that. All right, what else could I do?
4 times the quantity of natural log 2 to the -%.
Say again?
So what if 4 times the quantity of 5 natural log 2 to the -1?
Oh, okay. So just basically put this all to the -1.
Put the 5, I mean, like, bring it up.
What do you mean?
Do like natural log 2 to the 5th.
Yeah, that's what I did. That was what I did. I'm putting 5 in as a power to the 5th 32. Like, is the what's on the right better? No. I mean, they're the same. But again, I just couldn't help myself using my powers, right? My mathematical powers. That sounded funny. All right. This is a note. I'm not doing an example of this, but I want to just point this out to you. Okay? And this is also in your book there. I typed it up so that it was more easily displayed on the TV, but if you're differentiating a natural log and there's an absolute value next to the natural log, you can just do it as if it didn't have an absolute value on it, okay? I mean, the values of the domain is going to be affected, but the derivative is not going to be affected. and I didn't want to do another example because it's the same as the other natural log examples that we did, but just keep this in mind. When you see this, you can differentiate these just like those absolute values weren't there. It's not going to really affect your derivative, okay? Something I wanted to point out, but I didn't want to go through. Here's where I'm talking about the implicit differentiation, okay? Because when you have the next kind of example, which is this, I know that's very small. But what we have is a double situation where the base is some type of polynomial and it has a variable in it, and the power. In all the other examples we looked at, either the base was a constant or the power was a constant. But now we're going to put variables in both places. And so this is where we're really basically doing implicit differentiation because I have multiple variables in different places. Okay? And so I'm going to give you the steps that they want you to follow. Essentially what we're going to do is take the derivative of both sides, and because when I take the derivative of y, it requires me to use chain rule, I will end up with a y prime and a y, and then we're going to resubstitute it. So you take the natural log of both sides first. What we're going to do is, the reason we ever take the natural log of both sides is to get rid of the powers. Because when I take the natural log of the right-hand side, that power is going to come in front. So just the opposite of what we did with that 5 and 2 and made it 32. And then we won't be dealing with any more powers. Okay? The problem is going to be you're going to have other rules that you're going to need to use. All right. So then after I take the natural log of both sides, what you've got to do is simplify that, and that's what this is. The right-hand side is when the power comes down. That's what that's saying. And then you're going to differentiate. And so what you're going to end up with is you're going to have a polynomial multiplied by another polynomial, and so you're going to have to use product rule. Okay. The left-hand side is going to be easy because you got y by itself. But you're going to have the product rule on the right-hand side, and that's where it could get a little bit hairy. How that happened with that. Okay, back to this. All right. And then you're going to solve for y prime. And then lastly, because there's going to be a y in my work, you're going to substitute y back in, if necessary. So we're going to use the original equation that they give us, that y equals that whatever, and we're going to plug that back in because there's going to be a y in our formula. Okay. And here's an example that I'm talking about. This is example 12. So again, our problem here is that I have variable, variable. And we want our final answer in terms of x. We're differentiating with respect to x. So that's why we end up doing that sort of implicit differentiation on the left. So first move, take the natural log of both sides. Again, we want to bring that x minus 1 down. And that's what taking the natural log of both sides will do. Where did it go? Okay. So when I take the natural log of this side, this x minus 1 comes to the front. I mean, technically it's still here, but I skipped a step, right? And then I have the natural log of y. And so what we're going to do now is differentiate. So I started you on this. Go ahead and differentiate this yourself. And just do the first step after this. Don't keep going. Just do the first step after this because I want to make sure we're all on the same page first. Since we are differentiating with respect to x, it's here that I'm worried about, okay? Right? Because if I take the derivative of natural log of y, it's 1 over y. Except because it's y and not x, you have to also then take the derivative of y. So it's kind of chain rule because it's, and that's where I say it's sort of like implicit differentiation as well. So this is where we should be, okay? So it's 1 over y, but it's also multiplied by y prime. And so this is why I'm going to have to substitute back in for y eventually, okay? Again, you probably have this opposite. I've learned that you were taught it the opposite direction of me, which is fine, whatever. It's the same thing. I took the derivative of this, which is 1, times that, and then the derivative of this, which we did on the other problem already, I think, right? 1 over x squared plus 1, chain rule, and then the derivative of 2x, and that's the same thing. Okay, question, yes?
Why did you put y prime over y? Why did you put 1 over y?
Okay, because since we're differentiating with respect to x, you must also take the derivative of y, because it's chain rule.
So would that be the same as dy?
Yes, you could write dy dx, and that's something we're going to talk about moving forward. Like, if you wanted to rewrite, I made a presentation over the weekend. Yeah, so if you wrote it like this, that's fine too, same thing. Okay, I don't know what your preferred, notation is, and the truth is that it's the same thing. And so, back to your question, Liza, the reason that you have to differentiate the y is because it is chain rule. Since we are differentiating with respect to x, that's why I say it's like implicit differentiation. Since it's all, we have to also then take the derivative of y. So, and the other thing to keep this in mind, we're trying to find what y prime is. So if you never have a y prime in your equation,
Yeah, okay.
you see what I mean?
Yeah.
Like, so it's sort of telling you that we're trying to find y prime anyway, and if you didn't chain rule it, you'd never have y prime. Okay? And we're not solving for y because we know what y is. We're trying to solve for y prime. Okay? Good on that? Sure. Any questions on this? Am I right? You have it in the opposite order?
I don't.
You don't? Oh. It's fine. It's totally fine. They're equivalent values. Okay. The other thing that I would say in this particular problem, well, if you follow the procedure, you're solving for y prime. So that was the reason I used y prime instead of dy over dx. But again, they're the same thing. It doesn't matter. All right. Next page now. Yep.
Are we gonna multiply?
Oh yeah, no. Next page is like continuing because I ran out of room. Yeah, same problem. We're gonna keep going. Let me see if I just rewrote it again. Okay, no. What I did now is I get y prime by itself. Okay, so I'm gonna multiply both sides by y. So this is where I'm at. I'm getting y prime by itself. And so this is, we can't. The direction give us the answer in terms of x. Well, this is where I have to substitute in for y. All right, we already know what y is. They told us it was x squared plus 1 to the x minus 1. So that's where I substitute that back in, because both of these, this is the original y, and this y equaled that. And so that's where you substitute that. Okay. So when you get problems like this, there's a lot more opportunity to make a mistake, right? Because there's so many more things going on. We've got product rule, we've got logarithmic power rules, we've got substitution, we have implicit differentiation, right? Like, there's a lot going on. But this is my final answer. Okay? Questions?